So let's talk a little bit about the periodic table then. And so the periodic table was devised by a number of people, but probably most famously, it's the Russian chemist Dmitry Mendeleev. And in Mendeleev's periodic table, we saw elements that were being ordered by increasing atomic mass. And that left open the room for periodic properties. Now, the periodic table ended up changing over time, where instead of going from increasing atomic masses because of the lack of knowledge of protons, we end up seeing them ordered in or increasing atomic number, where we have arrangements of periods, the horizontal rows of the periodic table, and groups or families, the vertical columns of the periodic table. And so this was kind of the basis of that other activity, the periodic table mystery, which was looking at some of the aspects of the periodic table and how to identify them. Now, we didn't get a chance to talk about this yesterday, so I wanted to kind of draw your attention to a couple of key aspects, key attributes that we should familiarize ourselves with. First of all, there are some common families that we need to acquaint ourselves with. The first of which is group 1, which technically starts with hydrogen, although hydrogen is not considered to be an alkali metal in the pure sense. But group 1 here, these are the alkali metals. Alkali metals are known for having some very interesting chemistries. In particular, they are very, very reactive with air, and they are very, very reactive with water. In fact, the reactions with water can be downright explosive if the circumstances are correct. These are substances that are usually stored in oil or in kerosene or in some kind of otherwise inert atmosphere, because they will react with the oxygen in the air. They will react and rip hydrogen off of water. So we gotta be real careful about their storage. Closely related to those, if we go just next door, we have, these are the alkaline earth metals. And these ones are characterized primarily by they are also reactive with the air. They are also reactive with water, but to a much lesser degree than the alkali metals are. The alkali metals are very explosive in their reactivity. The alkaline earth metals are not as much so.
And all of the alkaline earth metals, all of them have a -2 charge, is that correct?
Yes.
Okay.
Well, excuse me, +2.
Oh, +2?
+2.
Okay.
And we'll get more into the dynamics of that when we get into chapters 3 and 4. Okay. But yes, there are some familial traits that we will see in terms of their reactivity, their ability to form ions, and so on.
Okay.
Moving on, let's grab this big group here. Here in the middle, this big group of elements are known collectively as the transition metals. Now, transition metals have a wide variety of reactivities associated with them. Some of these are quite reactive. Some of these are lesser in their reactivity. Overall, they are far less reactive than the alkali or the alkaline earth metals. And the other thing that we should notice about them is that they have some coloration to them. these are metals that have the possibility of not being silver. And when they dissolve in water, can make some really colorful solutions. They have the possibility of having multiple charges. And actually, we'll see that in some ways, elements like tin, lead, bismuth, polonium, tend to act more like transition metals than traditional metals. Tin and lead, for example, are well known for having variable charge. Whereas even with gallium and indium and thulium, thallium rather, they tend to focus mostly on +3 charge. You might see them with a +1 charge, but it's a lot more rare. So that's a little bit less common of a trait. On the backside, so looking at some non-metal groups. On the non-metal side, we have the halogens, which is group 17 here. The halogens are kind of the analogs to the alkali metals. They are highly reactive nonmetals. Now that they don't really have air reactivity or water reactivity, but they do have a good bit of reactivity overall. They form a lot of covalent compounds. And that puts them in very stark contrast to this last group. The last group here, which we'll highlight in pink, these are the so-called noble gases. And these are known for their incredible lack of reactivity. Now, there are other family names in here. The oxygen group, for example, is often referred to as the chalcogens. So basically, put a couple of C's in there, chalcogens, for the oxygen group. But the oxygen group doesn't have as much consistency in their reactivity as the halogens do. Yes, oxygen and sulfur, and to a lesser degree selenium, are reactive. In fact, oxygen is the most abundant element in the Earth's crust because of its reactivity with all of the different metals that make up the Earth's crust. But the gap between oxygen and sulfur, and the gap between sulfur and selenium, are pretty large in terms of their overall reactivities. And so sulfur is much more predominant as a stable element in the Earth's crust, just sitting there by itself, than it is as a reactive component. And selenium, it's much more of a trace element. It's present, but in significantly smaller quantities. Now, the last thing I wanted to point out to you, I've alluded to this in the past. I want to make it clear now. There are a series of elements that are naturally diatomic. And they are hydrogen and what I call the 7 that form a 7. So if you look at hydrogen and these 7 nonmetals, starting with nitrogen, working your way down through the nonmetallic or metalloid halogens, these substances are naturally diatomic. And what that means is that these substances will naturally on their own pair up with themselves and as an element exist in a pair. So we don't experience hydrogen as just simply H. Hydrogen always exists in its elemental form as H2. We don't experience fluorine as just F. It always exists as F2. And so when it comes time, especially when we start getting into balancing equations and recognizing chemical reactions, that's an important thing to understand. If I'm given a word equation that says hydrogen reacts with fluorine to make hydrogen fluoride, I have to understand that the hydrogen and the fluorine that we're talking about there are not just H and F, they're H2 and F2. So those substances are the ones that we need to kind of look out for. Because if we fail to recognize that quality, that characteristic of them, we're going to lose something about them. We're going to make mistakes in terms of quantifying their reactivity.
Silly question.
Yeah.
You said that they always basically happen in two. So why does oxygen and water only have one if it doesn't like to be by itself?
Well, so what's happening there is oxygen forms a double bond with itself when it's diatomic. When oxygen bonds in water, it's
Hmm.
taking those two bonds that it would have made with itself and making one bond with hydrogen and a second bond with another hydrogen.
Okay.
So it still has two bonds, now with two different things instead of with itself.
Oh, okay.
So that we'll get more into that level of reactivity in chapter 4, but the overall concept is kind of the same. There is a set number of bonds that atoms that elements are seeking to make.
Hmm.
And if it can get it from itself, great. If it doesn't get it from itself, then it goes and seeks it out from others. And so basically all that's happening in water is hydrogen is replacing the bonds that oxygen was going to make it to itself.
Okay, so if there's not enough hydrogen, then it'll basically the oxygen will basically just form with itself. Then, like if there's not enough hydrogen in the mix, the oxygen won't have anything to stick to, so it'll just form with itself.
To some degree, yes.
Okay.
It's we're in danger of oversimplifying it a little
Okay.
bit.
Okay. No, that's fine.
But yeah, certainly when we get to chapter 4, we'll get into the kind of the impetus for why do things bond, how do they bond, what's the driving force behind the bonding, that kind of stuff.
Okay.
All right, any other questions here before we move on?